Hello and welcome to the Introduction to Traffic Flow Theory, Part 3. We'll be focusing on queuing theory in this lecture. The objectives for this lecture on queuing theory are to present the tools of the trade for traffic flow theory that include cumulative arrival and departure curves and the basics of queuing theory. By the end of this lecture, you should be able to observe travel times and delays on queuing diagrams. We will do some examples, including an application to an incident on a freeway. And then I'll show you how the combination of time-space diagrams, which we learned about earlier, with queuing diagrams can present a three-dimensional model of traffic flow theory. So in transportation, just like in life, there are lots of queues. Queuing means basically waiting in line. And so what we'll be doing is studying some congestion phenomena that occur in queues. And the basic premise is that we have objects, typically in transportation, they're vehicles, passing through a point with a restriction on the maximum rate of passage. So you can think about queues that might happen at a grocery store when you're waiting to check out, in an airport when you're waiting in line to check your bag or go through security or pick up your bag or to enter the airplane, or in public transportation to enter a bus, or perhaps you're waiting at a taxi stand for a taxi. You might be waiting for an elevator in a building. These are all examples of queues. And the basic model as shown in this figure include some sort of input process, a storage area, which is where the queue sits. In traffic, that might be a turning lane, that might be an on-ramp to a freeway, that might be a taxiway at an airport. Then there's some restriction that we sometimes call a bottleneck that restricts the rate, the maximum rate of passage. And then that is, once we observe that, that's the output process. So you have input, storage, a restriction, and output. And you can observe these processes. You can use standard models for these processes, and you can make some approximations as well. The basic ingredients of queuing include customers, which might be travelers or vehicles, and that translates to arrivals and the arrival process that I just mentioned. Sometimes the restriction is called a server, and sometimes the mechanism that serves the arrivals is called the service mechanism, and sometimes the output process is referred to as departures. So you can imagine at the grocery store, you're waiting in a queue to check out your groceries. And so the input is the rate at which the customers are arriving at the check stand. The storage area is the area in advance of the person who's checking you out. The restriction is simply the rate at which the checker can process the items over the scanner. And then the output would be the rate at which the customers are departing from the check stand. And so this queuing is really an exciting field. In transportation, you can see queuing in action where airplanes are taking off on a runway. If you're paying a toll at a toll plaza, I mentioned waiting for an elevator, waiting for a taxi, ships at a port waiting to be loaded or unloaded, water being stored in a reservoir, the processes at the grocery store that I mentioned. And the queuing principles are even used in telecommunications, in the internet, and electrical circuits as well. So the word server actually began in queuing theory before the computer server concept was developed. We're interested usually in several different key parameters for planning and design purposes and for optimization. Some of those things include the maximum length of the queue, the typical time spent in the queue, and so we'll see how to calculate those key parameters. So here's a way of visualizing how queuing theory works. First, we start with the conservation principle, and that means basically that customers don't disappear. Once they enter the system, they will depart the system, and that the arrival times of the customers, which I'll show you in a second, completely characterizes the arrival process. And then what we what we'll do to visualize this is we'll use an NT axis, where the y-axis is the number of accumulation, the number of arrivals, and the x-axis is time t. So the idea here is each time a customer arrives, you simply record their arrival time. So I've shown the example here for several arrivals. Arrival 1 arrives at T1, so the number of accumulated customers jumps up by 1. And then at time 2, customer number 2 arrives, so the stair-step function shown in this graph increases to 2 at that time. Similarly, at times T3 and T4, customers 3 and 4 arrive. And so in this case, I'm just showing that the customers are not necessarily arriving at equal time intervals. You're just recording their arrival time. So the arrival curve is shown as the blue stair step. So this is something that you could observe, or perhaps you're given some data that tells you the arrival time of these customers. So the conservation principle is very important. You can't have more customers departing than they are arriving. Also, you'll see this later, and I just want to mention that you can't depart the system before you arrive. And so that's just something to remember when you're solving these kinds of problems, from my experience. So a few more points about the arrival process. We have a function that I'm calling j here. It's equal to the a of t. It increases by 1 at each t sub j. The observer can record the arrival times. The inverse t equals a to the minus 1 of j is the time that the jth object arrives. And so we're talking about integers here. So each stair step is the same height because we're counting individual arrivals. And you might see this is a short time period, a small number of arrivals. If we're talking about a whole day or a month or a year, then the stair steps would be so small that it would essentially look like a continuous curve that is then differentiable. So in order to approximate these stair steps, you can draw the curve through the midpoints of the stair steps. So let's talk about the departure process. We've seen the arrival curve a of t. And imagine that you're an observer. If we're talking about a grocery store check stand, you can simply see what time customer number 1 departs. That's t prime sub 1. And so the time in the system for customer number 1 is t prime sub 1 minus t prime, minus t1. So then you have the departure time of customer 2, t prime 2, departure time of customer 3 and 4, t prime 3 and t prime 4. So you might notice in this system here that the customers are staying in order. So customer 1 arrives first, also departs first. So you can construct the departure curve by recording simply the departure times. Okay, so now there are some things that we can observe. We can analyze this system based on these two curves, the arrival curve a of t and the departure curve d of t. Let's assume that the system is empty at t equals 0. So we're starting with an empty system. So the vertical distance at any time is the queue length in number of customers at that particular time. So where on the curve we're showing q sub t, q of t, you can see that there are a of t minus d of t customers in the system at that time. Remember that a of t and d of t can never cross, because you can never have more customers departing the system than have arrived. And usually in transportation, we use a system called first in, first out, or FIFO. That means customer number 1 enters first, customer number 1 departs first. So usually in a simple queue like this, we assume first in, first out, or FIFO. So the horizontal distance is the waiting time for the jth customer. Okay, so you can see for customer number 2, w sub j is just t prime 2 minus t2. And then, for example, at t 4, you can see that there are 2 customers in the queue. It's just the vertical distance between the blue and the pink curves. So horizontal distance is time, vertical distance is number. So the vertical separation between the two curves is the number of customers in the queue at that time. And the horizontal distance between the curves is the service time for that particular customer, customer number. I just emphasize here that A of t and D of t can never cross. Just imagine that A of t is made of something very strong, like concrete or steel, and the departure curve D just bumps up against the arrival curve and can never go above it. Students quite often make mistakes in solving problems along these lines. So as you zoom out from this queuing diagram, I'm just highlighting that this horizontal strip of unit height and width W sub j is something it's an area that we can calculate. So the area of that rectangle is just W sub j times the height, which is 1. So it's just W sub j. So what we can really do to determine the total delay occurring in the system for a particular number of customers is take the integral of the area between the two curves. Or in this case, we're just adding up those rectangles. So as we'll see when we do some examples later, we'll use the area between the curves to calculate the total delay, and that's one of our important parameters that we're interested in. So similarly, if you remember one of your first calculus classes, as I just said, you can add up the horizontal strips to obtain the total delay. And that's the total time spent in the system by a particular number of vehicles. You can also flip that around, and you can calculate the total time spent in the system by all customers during a specific time period by adding up the vertical strips. So the total delay is just the area between the two curves. So this is kind of to summarize everything. The total delay is we sometimes call W, which is in units of numbers of vehicles times time, usually vehicle hours. Of course, vehicle minutes is also fine. We can calculate the average time in the queue for all the arriving customers. It's just the total time divided by the number. So that's lowercase w bar, which is in units of time, seconds, minutes, or hours, which is the total delay, capital W, divided by n, the number of vehicles. So we have the averaged time in the queue. We can also rewrite that equation. Capital W equals lowercase w bar times n. The average number of customers in the queue is something that we're also interested in. Capital Q measured in units of vehicles or customers. It's an integer count of the number, and that is capital W, which is in units of vehicles times time, divided by capital T time, the total time that we're observing. And if you rewrite that equation, you obtain W equals capital Q times capital T, which is equal to lowercase w bar times n, as we just found in the line above. So we can say that capital Q equals Wn divided by T. And sometimes we call n over T, which is essentially the flow, number of customers per time, as we talked about before. We can define that as an arrival rate, and it's often notated as lambda. So if we substitute lambda equals n over t into the equation, we have Q, capital Q, which is the average number in the queue, is lambda times W, and that's known as Little's formula in the queuing literature. So that's something to recognize that we're using a theory developed by Little, where we say that the average queue length is the average waiting time times the average arrival rate. And this is a very important principle for transportation, and we'll see how this works in some examples. The example we're going to start with is about an incident, but first I need to tell you what an incident is. You've probably seen crashes, breakdowns, and other things happening out on the roadways. So an incident is defined as a crash, breakdown, and other random event that occurs on the highway, usually either blocking one or more of the lanes on a roadway, or if it's not blocking, it's something that causes rubbernecking, which can slow down traffic. Incidents contribute to more than half of the congestion on our highways. Incidents are things that we prefer not to happen. And so what we try to do is minimize the number that happen and then also minimize their duration. So quite a bit of effort is spent trying to prevent incidents from occurring and in managing them if they do occur, minimizing the time that they're present on the roadway. So sometimes these incidents can lead to major road closures that expose everyone, the emergency responders and the drivers, to hazardous conditions. So sometimes one incident may happen that leads to a queue in which additional crashes can occur. And they basically are costly to society because they reduce productivity, they cause delay, and they divert maintenance resources. Okay, so incidents are things that we focus on in transportation engineering. So let's just use the principles of queuing theory to try to analyze some aspects of incidents. So here's a queuing diagram where N is on the y-axis, T is on the x-axis. So we have the cumulative number of vehicles arriving at a particular point along the highway. And then time is on the x-axis. So what's happening here is that the black line is that I've labeled demand. That's the flow on the freeway that is occurring. And we're going to talk about what happens when an incident happens. We call this diagram the life of an incident. So at time 1, an incident occurs. And let's just say that that incident blocks one lane. And so the flow that is able to pass by the incident is much lower than the demand. So the slope of the line above the words incident flow, that's the flow that is able to pass once the incident occurs. Time number 2, usually it takes a while for the incident to get reported to the traffic management center. Time 3, a little bit later. The operators at the traffic management center use video cameras, CCTV cameras to verify incident has occurred. They will dispatch emergency vehicles to respond. And then at time 5, which is a few minutes after the incident happens, the responders arrive there. So it could be a tow truck, it could be an ambulance, fire truck, could be something even more depending on the severity of the incident. So by the time the responders arrive, some delay is already happening. So you can see that the green zone is the area between the demand curve on the top and the incident flow departure curve on the bottom. At time number 6, a little bit later, let's say the incident is cleared. So as soon as that incident clears, traffic will start flowing at a high flow, which I've called here capacity flow. So that's higher than the original demand flow. So you probably, if you've experienced an incident on the highway, or if you've experienced congestion, you get the feeling that once you pass by that blockage, vehicles will accelerate and will start flowing at a higher flow. So as soon as point 6 happens, traffic will flow at capacity until the departure curve intersects with the demand curve, which means that the queue is cleared. So congestion ends at time 8. That's quite a bit later than the time that the incident is cleared. It takes a while for the queue to clear. So that's a little bit of an example of what the life of an incident looks like. And we'll talk a little bit more about some of these calculations in some of our examples. So I'd like to show why it is useful to think about reducing or minimizing the duration of an incident. You can see on this slide that the duration of the incident is from time 6 minus time 1. And so what we're usually trying to do is minimize that horizontal distance, minimize the duration that traffic is flowing at that lower incident flow. So next, I've just shown an example here. What happens if we cut the duration of the incident in half? You can see that the delay, the area of that green triangle, is only now 25% of what it was before. And so it's very beneficial to reduce the duration because it has, by cutting that in half, we save 3/4 of the amount of time that was imposed on traffic. And I'll do some calculations of that using a real example next. So here is a similar situation. The demand flow is the pink line. The incident flow is the yellow line. And so in this case, let's assume we have a 3-lane freeway. Each freeway lane has a capacity of 2,500 vehicles per hour per lane. So the total capacity of this freeway is 7,500 vehicles per hour. The pink slope, this is an NT curve where the y-axis is the cumulative number of vehicles, the x-axis is time, and traffic is flowing at the slope of the demand flow, which is lower than the capacity flow. And I'm just showing this blue curve here for reference. So traffic is actually flowing at the pink slope of 6,000 vehicles per hour. That's a little bit lower than the capacity. At time 0, an incident occurs, and the incident flow is half of the demand flow. So for 60 minutes, you can imagine that the freeway is blocked, and so that traffic can only flow during the incident at 3,000 vehicles per hour. As soon as the incident is cleared at time equals 60 minutes, traffic will flow at capacity 7,500 vehicles per hour, the steeper slope, until it intersects the demand curve, at which the traffic will simply continue flowing at that demand value of 6,000. So the total delay is the area shown by that shaded triangle, and we can calculate that. And the total delay, if you calculate the area of that triangle, is 270,000 vehicle hours. And by reading from the diagram, we can see that the queue lasted for 180 minutes. That's 3 hours. So the incident was cleared after 1 hour, but it took 2 more hours to clear that queue. And you can see from the y-axis that a total of 18,000 vehicles were affected by this incident. So there's a huge cost there. That delay is basically people's time, and people's time is worth money. And so you could calculate the dollar value of that delay by multiplying 270,000 vehicle hours times a typical value of time. But let's look what happens, similar to what I showed you a minute ago. What happens if we can reduce the duration of that incident by responding faster, by clearing it off of the highway faster? This is usually what we're aiming to do. So let's say that we can cut the duration down to 30 minutes. So we cut the duration in half. You can see that the demand flow is still 6,000. The pink, the capacity flow is still 7,500. So after 30 minutes, the incident is cleared. Traffic begins to flow at the capacity flow. And basically, the incident is cleared after 90 minutes. So the queue duration is now half of what it was. The number of vehicles affected is also half, it's 9,000, but the total delay is 25% of what it was before at 67,500. So just on a bar chart, you can see here the duration of the incident effects is cut in half, the number of vehicles affected is cut in half, and the total vehicle hours of delay in the shorter incident is basically reduced by 3/4. So there's a huge benefit to reducing the incident duration, and you can use a queuing diagram to determine those parameters. So next, let's look at what happens when we combine the time-space diagram and queuing theory. So this is a 3D version of traffic flow theory. Remember that a time-space diagram looks at one or more objects over time and space. Queuing theory looks at one point, and we focus on what is happening at that one point to those many objects or those many vehicles. So if we combine the two, we result in a three-dimensional surface. So time-space diagrams and queuing diagrams are both important. Queuing diagram is NT. N is the y-axis, T is the x-axis. Here on this diagram, this is a time-space diagram showing 5 vehicle trajectories where x is on the y-axis and t is on the x-axis. So what we can do when we have a time-space diagram, we can take vertical slices at T1 and T2. So you can see those light lines at time 1 and time 2 where I've taken a vertical slice. And then I'm translating the count of the vehicles over to the right to produce an NT diagram that's actually turned 90 degrees, where we're just recording at T1 the arrival time of vehicle number 3 and the arrival time of vehicle number 2. So the stair steps on the right hand side correspond with the intersection between the trajectories and the vertical line at T1. And then the solid stair step on the right hand side, that is n of x and T2, that corresponds with the intersection between the arrival of vehicles number 3, 4, and 5. So the stair step for 3, 4, and 5, you translate over to the right. So you can observe the distances traveled and the numbers passing a particular point. Okay, so remember, an NT is for a particular point. So this one shows the vehicle counting functions for nx of T2. So you can do horizontal slices at x1 and x2, and then you can translate those intersections down to an NT curve. This is basically what we use for a queuing diagram. So you can convert by slicing your time-space diagram and recording the times that at the slice that the trajectories intersected as the arrival times. So you can see, translating down for location x1, you have the n of t and x1 curve with the blue dashed lines for vehicles number 2, 3, 4, and 5. And now we can do the same thing for location x2, which is for the dashed step function, where you have the arrival times of vehicles number 1, 2, 3, and 4. Okay, so you can relate the 3 different types of curves. XT is the time-space diagram, NT at the bottom is the queuing diagram, and the NX diagram is not used in this course, but it's the third component that we described to you. So the basic theory has now been presented to you. We've presented earlier in part 2 the concept of creating a vehicle trajectory, and we've created time-space diagrams, and we can also study headways and flows. In queuing theory, I would like to just mention that there's some terminology that's used, and you can find this in the Mannering textbook. And basically the terminology is a coding for the characteristics of the arrival pattern, the departure pattern, and the number of departure channels. The simplest type of queuing analysis occurs at what's called DD1 queuing discipline, which means a uniform or deterministic arrival function and a deterministic or uniform departure function with one channel. So this is what we can illustrate graphically. We'll say a few words about some of the other types of queuing disciplines at the end, but DD1 is what we'll focus on for these upcoming examples. So the first example, we're looking at how vehicles arrive at a park. So typically when you go visit a state park or a national park, you may have to enter on a roadway and stop at a gate where you pay your fee or where you pick up a map or brochure from the park attendant. So in this example, it's essentially a one-lane road going into a park, and the park opens at 8 o'clock a.m. and vehicles begin to arrive at a rate of 480 vehicles per hour. So there's a peak of 20 minutes, and after that initial 20-minute period, so at 8:20, the arrival flow declines to 120 vehicles per hour and continues at that level for the remainder of the day. And so the question says, if the time required to distribute the brochure is 15 seconds, and assuming DD1 queuing, that means uniform arrivals, uniform departures, and one lane, describe the operational characteristics of the queue. So let's take a look at this example. So basically, to solve these problems, we draw the queuing diagram. And so everything you need to answer this question is shown in this diagram. So the x-axis is time in minutes, and the y-axis is n, or the number of arriving vehicles. So we're just told at 8 o'clock, which is time 0 in this particular example, the vehicles begin arriving at 480 vehicles per hour. And so in the first 20 minutes, a total of 160 vehicles arrive. So that's the green triangle. So at 8:20, the arrival rate drops to 120 vehicles per hour. And so the slope of the green line drops. So I'm showing the arrival curve in green here. And there are a couple things to notice. You can write an equation for the initial portion of the arrival curve, and that's 8 times t in minutes. And then the equation for the second component of the arrival curve is a equals 2 times t in minutes. So you can write the equation of that line as 160 plus 2 times t minus 20 for that second portion, if you like. So the other part of the problem statement is about the service rate. So the person at the entrance to the park is distributing brochures every 15 seconds. So you can see that the vehicles will be served. There will be four vehicles served every minute. So the departure curve slope for the initial period could be written as d equals 4 times t in minutes. So there's something very important to notice at the time when the departure curve, the red line, hits the green curve. Because remember before I said that you can't have more departures than arrivals. So what happens when the departure curve intersects the arrival curve at t equals 60 minutes is that from then on, basically the vehicles are arriving at a rate lower than the service rate. So essentially, starting at t equals 60, the vehicles are being served just as they arrive. So there's no delay, and because the arrival rate is lower than the service rate, 2t is less than 4t, there's actually excess capacity starting at t equals 60. But let's take a look at this diagram and see some of the components. You can see, for example, just from looking at this curve, you can answer questions, a lot of different questions. What's the queue length at t equals 10? So that's just a of 10 minus d of 10. So 80 minus 40 is 40 vehicles. The key components, the key operational characteristics of the queue that were asked in the example question are basically the longest vehicle queue and the longest vehicle delay, as well as the total delay and the average delay. So on this diagram, you can see all that. We've labeled the vertical line at t equals 20. That's the longest vehicle queue. So you just calculate a of 20 minus d of 20. So that's just 160 minus 80. So the longest vehicle queue is 80 vehicles. So you need to make sure that you have enough space in your design of your roadway for 80 vehicles to be queued at that time, worst case. The longest vehicle delay, assuming first in, first out rules, happens to vehicle number 160. And basically, to calculate that horizontal distance, remember that's time, it's just d of 40 minus a of 20 for the 160th vehicle. So that's 20 minutes is the longest time that a vehicle has to wait. Okay, so those are shown there in yellow, the the longest queue is 80 vehicles. The longest vehicle delay is 20 minutes. So we can calculate the total delay as the sum of the two right triangles. And so it's just 1/2 base times height plus 1/2 base times height. For those two triangles, the triangle on the left, 1/2, the base is 20, the height is 80. And then the triangle on the right, 1/2, the base is 40 and the height is 80. So if you sum up those two values, you will obtain the total delay. And you can take the total delay and you can divide by the number of vehicles. 240 vehicles are affected by this, and you can then determine the average delay. So you can answer quite a number of questions. This picture also shows the delay of the 100th vehicle to arrive. So there are a wide range of questions that you can answer once you have the diagram drawn. So that is the end of the example 5.7. Let's do another example. This is vehicles arriving at a parking lot at 6 a.m. at a rate of 8 per minute. Due to an accident on the access highway, no vehicles arrive between 6:20 and 6:30, so the arrival rate is 0. And then at 6:30, continuing on, vehicles begin to arrive at a rate of 2 per minute. The parking lot attendant processes incoming vehicles, collects the parking fees at a rate of 4 vehicles per minute throughout the day. And again, assuming DD1 queuing,
I know that one.
Determine the total vehicle delay. So again, you draw the diagram, an NT diagram, so N on the y-axis, T on the x-axis. So this is what the arrival curve looks like. So the vehicles are arriving from 6 to 6:20 at 8 vehicles per minute. And from 6:20 to 6:30, there are 0 vehicles arriving. And then after 6:30, they start arriving at 2 vehicles per minute. The departure curve, we were told that the vehicles can be served. So by departure curve, I mean the vehicles that are departing from the entrance booth into the parking lot, and they can be served at 4 vehicles per minute throughout the whole day. So as you can see, there is a point at 6:50 in the morning where the departure curve bumps into the arrival curve. So never allow the departure curve to go above the arrival curve. So starting at 6:50, even though the capacity of this parking attendant is 4 vehicles per minute, they only need to serve at 2 vehicles per minute. So it is below capacity starting at 6:50 a.m. But between 6 o'clock and 6:50, you can see that there's a space between the arrival curve and the departure curve. And so the area of that shape is the total delay. So that is not just a simple right triangle. It's several different triangles stuck together, but we can calculate the area of that to determine the total delay. We'll also report on the other important parameters of that bottleneck. So what I'm showing is how to calculate the area. You can do it any way that you want, but what I'm going to do is call this area number 1, this red area, and this right triangle, this purple right triangle, is area number 2. And so to calculate our desired area, we take the red area number 1 and subtract the purple area number 2 to obtain the area that we want. So I've shown the calculations here. For the red area, it's 1/2 times 20 minutes is the base, and the height is 160. Then I calculate this rectangular shape that occurs from 6:20 to 6:50. So the bottom of that rectangle is 30 minutes. The height is 160. And then there's just this little triangle left on the top. 1/2, 20 minutes between 6:30 and 6:50, and then the height is 40 vehicles. And then we subtract the area of the purple triangle, which is 1/2, and the base is 50 minutes, from 6 o'clock to 6:50, and the height is 200, because by 6:50, a total of 200 vehicles have arrived and departed. So the total area of our area, the shaded red area, is 1,800 vehicle minutes, and that you can convert that to 30 vehicles per hour because there are 60 minutes per hour. And we can calculate the average delay because of the 200 vehicles, each one experiences an average of 9 minutes of delay. And then there are a couple more things that we can calculate here. The maximum queue occurs at 6:20, and that maximum queue is of 80 vehicles. So we would need to have, again, enough storage area for 80 vehicles. And then the maximum delay occurs for the 160th vehicle. That maximum delay is 20 minutes. So those are the important parameters for these examples. So just a couple more words about queuing theory. We typically call the arrival rate lambda, and we measure that in units of vehicles per unit time. And some assumptions that we make about arrival patterns. We're talking most of the time in transportation about uniform deterministic arrivals. And sometimes we're talking about exponentially distributed time intervals derived from the assumption of Poisson distributed arrivals, and we'll do a quick example about that in a minute. The departure patterns, we usually call those mu, again in units of vehicles per unit time, and sometimes those are also assumed to be, most of the time for this class we'll be talking about uniform departures because of they're derived from uniform arrivals, and sometimes we'll use the Poisson distribution. I already talked about the first in, first out queuing discipline, indicating that the first vehicle to arrive is the first vehicle to depart. Sometimes we have last in, first out queuing disciplines. Sometimes, for example, in boarding airplanes, the airlines might choose to board the people who were sitting in the rear first. So those would be and you board the people in the front last, and then they would exit first. So that could be a last in, first out discipline. Sometimes also on a 2-lane road, if there's a slow vehicle and vehicles are queuing up behind that vehicle, sometimes if you're the vehicle right behind the slow vehicle, you're the last one that is able to pass. So sometimes that is also considered a last in, first out queuing discipline. But for almost all other traffic-oriented queues, like those at traffic signals or on freeways, the first in, first out queuing discipline is the most appropriate. We already talked about what the DD1 queuing is, deterministic arrivals and departures with one departure channel, and we already saw how those could be analyzed on as a graphical solution. We can also have non-uniform arrivals, which are called stochastic arrivals, and that's sometimes considered to be more realistic because traffic is rarely uniformly distributed. And if we're assuming variable arrivals, we have to make some assumptions about the arrival patterns using some sort of a distribution. So MD1, if we have stochastic arrivals and deterministic departures, we usually consider exponentially distributed times between the arrivals of successive vehicles, and we refer to this as Poisson arrivals. So for an isolated traffic signal, this would apply a traffic signal that doesn't have other traffic signals near. And basically the Poisson model formula looks like this, where we approximate non-uniform flow with the probability of having n vehicles arrive in time t using this equation, lambda t to the n times e to the minus lambda t divided by n factorial. T is the duration of the time interval over which vehicles are counted. Lambda is the average vehicle flow or arrival rate in vehicles per unit time. And E is the base of the natural log, 2.718. Let's look at an example. If an observer counts 360 vehicles per hour, that's a rate or a flow at a specific highway location. and we assume that the arrival of vehicles is Poisson distributed, we're asked to estimate the probabilities of having 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20-second interval. So we can use the formula that I just showed you. That's equation 5.23 in the book. Lambda is 360 vehicles per hour, or 0.1 vehicles per second. We have to convert that. And then t is 20 seconds, since that was asked in the problem statement. And so we use equation 5.23, and so we can find for the probability of 0, 1, 2, 3, and 4, using the equation. For example, the probability of 0 vehicles arriving over the 20-second interval is 0.135. The probability of 1 or 2 is 0.271. The probability of 3 vehicles arriving over that 20-second interval is 0.18, and the probability of 4 vehicles arriving is 0.09. So I suggest you try using that formula and see if you get the same answers. So to do the last part, for 5 or more vehicles, P of n greater than or equal to 5 is 1 minus P of n less than 5. So we can take the values that we just calculated and subtract them from 1, and we obtain 0.053. And this is kind of what it looks like graphically. The probability of 0, 1, 2, 3, and 4 vehicles arriving in a 20-second interval are shown as a bar chart. And then to the right of the red arrow is the probability of 5 or more vehicles. So obviously 20 seconds is a short time, so it's a low probability that 5 or more vehicles would arrive during that interval. So that's a quick example of a Poisson distribution. So the assumption of Poisson vehicle arrivals also implies a distribution of the time intervals between the arrivals of successive vehicles, known as the time headway, which we learned about before. To show this, note that the average arrival rate is lambda is q divided by 3600. So we get lambda in vehicles per second, since q is presented in vehicles per hour, and 3600 is the number of seconds per hour. So we can substitute lambda equals q divided by 3600 into equation 523, and we rewrite it like this. And the probability of having no vehicles arrive in a time interval of length t is equivalent to the probability of a vehicle headway h being greater than or equal to the time interval t. So the probability of exactly 4 vehicles arriving is p of n equals 4. Probability of less than 4 vehicles arriving is p of n is less than 4. That's p of 0 plus p of 1 plus p of 2 plus p of 3. And just like we did before in the example, the probability of n greater than or equal to 4 is 1 minus the probability of n less than 4, which is 1 minus p0 plus p1 plus p2 plus p3. So the amount of time between arrival of successive vehicles is shown here, e to the minus qt over 3600. And the distribution of vehicle headways is known as negative exponential or just the exponential distribution. So continuing the example that we did a minute ago, what's the probability that the headway between successive vehicles will be less than 8 seconds? And what is the probability that the headway will be between 8 and 10 seconds? So the probability of h less than 8 is 1 minus p of h greater than 8, which is 1 minus e to the minus qt divided by 3600. And so t is 8, q is 360. So that probability of h being less than 8 is 0.551. And the second part of the question, we also need to calculate the probability that h is greater than 10, and that's 0.36. So the probability that the headway is between 8 and 10 is 1 minus 0.551 minus 0.368, or 0.081. So that's a little bit of an exercise with the Poisson distribution. And we can do one more example. observer has determined that the time headways between successive vehicles on a section of highway are exponentially distributed, and that 65% of the headways between vehicles are 9 seconds or greater. If the observer decides to count traffic in 30-second time intervals, estimate the probability of the observer counting exactly 4 vehicles in an interval. Okay, so we're given this, that t is 9 seconds, and we're given that the p of h greater than or equal to 9 is 0.65, and that's equal to e to the minus q times t divided by 3600. And so what we need to do is solve for q. So we can rewrite the equation 0.65 equals e to the minus 0.0025 q. And so q is the natural log of 0.65 divided by 0.0025. And q is therefore 172.3 vehicles per hour. In seconds, that's 0.048 vehicles per second. So with a time interval of 30 seconds, x equals 30 times q measured in seconds, which is 30 times 0.048, or 1.436. So p of n, in this case p of 4, is x to the n times e to the minus x, or 0.0421. So just a few words about the other queuing disciplines. MD1, traffic intensity rho, is lambda divided by mu, the average arrival rate divided by the average departure rate. There are some equations here for average queue length, q bar, the average waiting time, w bar, and the average time spent in the system, t bar. So if you're called upon to calculate these are the equations you can use. M1, so where you have stochastic arrivals to stochastic departures, but still one channel. There are exponentially distributed times between the arrivals of successive vehicles, and it's the same thing we just talked about, Poisson arrivals. And the departure time patterns are also exponentially distributed, and there are some traffic applications, including at toll booths. Of course, most tolls are being paid electronically now, but sometimes there's a cash lane, and some drivers may have the correct change and can be processed quickly, and others may not. So in that case, a distribution of departures about some mean departure rate will result. These are the equations for MM1, where lambda is the arrival rate and mu is the departure rate, the average length of queue, average time waiting in the queue, and the average time spent in the system. So MMN queuing, where you might have more than one channel. In this class, we will focus mostly on having one channel. MMN queuing can be a reasonable assumption at toll booths or toll bridges, and also non-traffic but transportation applications such as security checks at airports, queuing at ports and airports, and so on. Also checkout lines and call centers and so on, where you have more than one check stand. These are the equations which come from the book for multi-channel queues, for average queue length, average time waiting in the queue, and average time spent in the system. The probability of having no vehicles, probability of having n vehicles, and the probability of being in a queue are also quantified here. So there are some limitations. The mean in a Poisson model, the average number of cars per time period must be equal to the variance, and there can be other cases where you might use an alternative model. So this is the end of traffic flow theory number 3. We thank you for your attention, and we hope you have a wonderful day.